Welcome to this video, where we will explore one of the strangest and most fascinating phenomena in quantum physics, quantum tunneling. Quantum tunneling allows particles to pass through barriers that, according to classical physics, they should never be able to cross. It's as if particles can cheat, ignoring the rules that govern the everyday world. Today, we'll explain quantum tunneling in simple terms, explore how it works, and look at its surprising implications for technology and nature. To understand quantum tunneling, let's first recall how classical physics works. Imagine a ball rolling toward a hill. If the ball does not have enough energy to reach the top, it simply rolls back down. Classical physics tells us that the ball cannot appear on the other side without going over the hill. Barriers are absolute, they cannot be crossed without sufficient energy. In the quantum world, however, particles behave very differently. Particles like electrons or protons are not just tiny balls, they also behave like waves. These waves describe the probability of where a particle might be found. When a quantum particle encounters a barrier, its wave function does not simply stop at the wall. Instead, the wave extends slightly into and even beyond the barrier, giving the particle a small but finite chance of appearing on the other side. This is quantum tunneling. A simple analogy is to imagine a ghost walking through a wall. In classical physics, walls are impenetrable. In the quantum world, particles have a ghost-like ability to pass through barriers, not by breaking them or jumping over them, but because their probabilistic nature allows them to exist on the other side. The particle has a chance to tunnel through, even if it does not have enough energy to climb over the barrier. Quantum tunneling is not just a theoretical curiosity. It is a real phenomenon that has been observed in countless experiments. One famous example is the scanning tunneling microscope, a device that can image individual atoms. The microscope works because electrons can tunnel between the microscope's tip and the surface being scanned, allowing scientists to detect atoms with incredible precision. Without tunneling, this groundbreaking technology would not be possible. Tunneling also plays a critical role in nature. In the Sun, nuclear fusion occurs because hydrogen nuclei can tunnel through the energy barrier created by their mutual repulsion. Even though the nuclei do not have enough energy to overcome this barrier classically, quantum tunneling allows them to fuse, releasing the energy that powers the Sun and provides light and warmth to our planet. Without tunneling, the Sun would not shine, and life on Earth would not exist as we know it. Quantum tunneling is also essential in modern electronics. Devices such as flash memory, tunnel diodes, and certain types of transistors rely on tunneling to function. As electronic components become smaller, tunneling becomes increasingly important, sometimes posing challenges for engineers trying to control unwanted tunneling in nanoscale circuits. Understanding and harnessing tunneling is key to the development of future technologies, including quantum computers. The mathematics behind quantum tunneling can be complex, but the underlying idea is simple. The wave-like nature of particles gives them a probability of appearing in regions that classical physics would consider forbidden. The thicker or higher the barrier, the smaller the probability, but it is never exactly zero. This is a radical departure from the deterministic rules of the classical world and highlights the probabilistic nature of quantum mechanics. Tunneling also raises deep philosophical questions. In classical physics, cause and effect are clear, and events are predictable. Quantum tunneling shows that particles can do things that seem impossible from a classical perspective. The universe at the quantum level is probabilistic, and events can occur even when they appear to violate classical rules. This challenges our intuition and invites us to rethink the fundamental nature of reality. In summary, quantum tunneling is a phenomenon in which particles pass through barriers that would be impossible to cross according to classical physics. It arises from the wave-like nature of particles and the probabilistic rules of quantum mechanics. Tunneling has real-world consequences in technology, nature, and our understanding of the universe. It allows electrons to flow in microscopes, enables nuclear fusion in stars, and plays a critical role in modern electronics. By understanding quantum tunneling, we gain insight into a world where particles can cheat the classical rules, where probability governs outcomes, and where the strange and counterintuitive behavior of the quantum realm becomes a source of real power. Quantum tunneling is a window into the extraordinary possibilities of nature, revealing that the universe is far more surprising and mysterious than our everyday experience suggests. Thank you for joining this exploration of quantum tunneling. As we continue to study the quantum world, phenomena like tunneling remind us that reality operates on principles that challenge our intuition and open doors to technologies and discoveries that were once thought impossible.